So here we go. This is the second part of the Wireshark series. In the first video, we covered the complete tutorial on how to use Wireshark. We covered the basics and we covered the packet navigation and dissection. Today we're going to analyze traffic with Wireshark. So let's discuss what do we have today on the agenda. First thing, we're going to see how we can analyze traffic and detect Nmap scans. So there we go, we have a typo here, we're gonna correct this. So Nmap scans, and we're going to take a look at how to analyze ARP packets, meaning we want to take a look at how attackers can perform ARP poisoning and man-in-the-middle attack. How can we detect this using Wireshark? So ARP poisoning plus MITM. They are closely connected actually, ARP poisoning and MITM. You need to, in order to conduct man-in-the-middle attack, you need, as a precursor, you need to perform ARP poisoning. So they are like ARP poisoning and then you have MITM. And third on the agenda, we're gonna analyze the HTTP, NetBIOS, and we're going to analyze Kerberos. We're going to take a look at the examples of these packets. How do they look at in a packet capture file? Additionally, we're going to take a look at DNS and ICMP packets. And of course, we're going to learn how to extract clear text credentials from FTP and HTTP. And lastly, we're going to take a look at how to decrypt HTTP packets. I have never found something better than this room to demonstrate the concepts we have discussed earlier. So we're going to go over the tasks, we're going to answer the questions, and hopefully guys, we'll be able to explain the idea. So first thing, let's jump over to the Wireshark, and from here we need to start answering the questions. So the first thing, we're going to take a look at the questions in task 2, where it is around Nmap scans. Let's scroll down. Okay. So while we answer the questions, I'm going to explain the concepts of every single filter we use in Wireshark. So the first thing is open the capture file exercise at the Nmap directory. So we're going to go to file, open, go to computer. So from here we should highlight where it is. It is the desktop. So Ubuntu desktop exercise. Okay. Nmap and exercise. Okay. So that's what we have. Now this is a packet capture file that represents Nmap or captured Nmap traffic, meaning there was a machine at point in time where someone was scanning this machine with Nmap. So they captured the traffic and gave it to you so that you analyze the packet capture and find out the nature of the Nmap scans performed against the machine. The first question is, what is the total number of the TCP connect scans? So as you know guys, Nmap has various types of scans. We can perform connect scan, stealth scan, UDP scan, TCP scan, right? In this question, we need to find out the total number of TCP connected scans, meaning we want to find out if the attacker has performed Nmap TCP connect scans. So to find out, we need to rely on what is called the TCP flags. As you know guys, in Nmap we have TCP three-way handshake, where the client sends a synchronization packet, as seen here in the examples. From packet 1 to 5 we have synchronization packets, and then we have reset acknowledgement, right? So the combination of synchronize, acknowledgement, reset, these flags can be used to filter or extract packets that would show Nmap or Nmap attempts. So first, let's see, we have to find out TCP connect scan. So to do that, we're gonna use this filter, TCP.flags. Okay, we're gonna use the TCP flags filter and synchronize equal to 1. So when the synchronized flag equals to 1, meaning we have a TCP connect scan combined with another condition. The other condition is that the server would need to send an acknowledgement scan. Okay, a TCP connect scan, the client sends a hello with the synchronize flag set, okay, and the server replies with acknowledgement. So the other condition for a TCP connect scan to be successful is tcp.flags.acknowledgement needs to be 0. Okay, and the last condition, the window size, tcp.window size needs to be less than or more than 1024. So TCP window size, we have a problem in this. So here it is not Windows, it is window. So here we have 3 conditions. We use them in one filter. The sync flag needs to be 1, the acknowledgement flag needs to be 0, and the window size needs to be more than 1024. So execute this filter, and here, as you can see, guys, Wireshark has extracted all of the packets that would indicate there was a TCP connect scan. As you can see, we see here a synchronize packets sent from this client with the IP address of 10.10.67 to the destination IP address represented by 10.10.47.123. So all of these are synchronization packets indicating that there is indeed an Nmap scan. The number of packets displayed here is 1000. At the bottom here, as you can see, guys, where hovering over with the mouse, the number of packets is 6544, out of which we have displayed packets that represent the filter we have just executed is 1000. Okay, next question. Which scan type is used to scan the TCP port 80? So if we filter the TCP traffic now, where the port equal to 80, we use the filter tcp.port equal to 80. Take a look at the nature of the packets. Okay, as you can see here, guys, to find out the type of Nmap scan that's used to reveal to port 80, we're going to take a look at the flow of the packets. The first packet, as you can see, we have a synchronization flag set, and then the host or the destination address ends with 123, replies with another packet where the acknowledgement flag is sent, and then the client send an acknowledgement flag, and lastly the server sends reset acknowledgement indicating that the three-way handshake is finished successfully. So this is typical of a TCP connect scan, a regular TCP connect scan, as opposed to TCP stealth scan. In a TCP stealth scan, the client only sends a synchronization, a packet, and then would never send an acknowledgement. That's the difference between TCP connect and TCP stealth scan. So we answer with TCP connect scan. How many UDP close port messages are there? Okay, so here UDP close ports. So basically here we need to find out the UDP scans on a closed port that indicate that the port was closed. To be able to do that, we're going to need to get the help or use ICMP filters, because UDP scans use ICMP packets. So we're going to use ICMP.type equal 3, that's the opcode, and ICMP.code equal 3. So this indicates that we are looking for UDP scans where the port was closed. And we have 1083 packets. The last question is, which UDP port in the 570 port range is open? Which UDP port in the 55570 port range is open? So basically here, to be able to find out the answer for this question, remember that we need to exclude the closed ports. To exclude the closed ports, it's going to be very easy. All we have to do is to use this filter that is not equal. So this is the not equal filter, meaning we're going to exclude all the UDP scans that resulted in closed ports. So we're going to type here UDP first, UDP, and so this is the filter. We're going to look for UDP packets and packets that satisfy both conditions, where the protocol is UDP and the port is open. We're gonna enter and we'll see we have 1445 packets. So which UDP port? Oh, okay, we'll have to find out the port now. Which UDP port in the 55570 range? Let's take a look here. So as you can see here, guys, if you take a closer look at the packets at the info section, we want to see a port that is between this range 55 and 70. So far these ports are out of range. As you can see here, guys, packet number 6294, the port here is 68 in the info section. This is the correct answer. This port falls in the right range between 55 and 70. Alright, in the next task we're going to answer, or we're going to take a look at the examples of how to analyze the ARP or ARP protocol, address resolution protocol. Okay, we're going to take a look at another PCAP file. So we're going to File, Desktop, Exercise, ARP. The file is exercise. Okay, so we have the file open now. The first question is, what is the number of ARP requests crafted by the attacker? So we're not only looking to extract the ARP packets, but we want to extract the ARP requests crafted by the attacker, meaning here there is a possibility of ARP poisoning attack. To extract the ARP poisoning, or the packets that contain ARP poisoning attack, we're going to use this filter. As you can see, we have 138 packets. Now to take a look at the source machine that is conducting the attack, we're going to have to take a look at an example packet. Take a look at this one, for example, and we scroll down to the address resolution protocol, expand this, and from here we can highlight the sender MAC address. It starts with 00 and ends with P4. This indicates, or this shows, the MAC address of the attacker that has crafted these ARP poisoning packets. Okay, what's next? Next, we need to find out how many requests the attacker has sent. So we're not only looking at the total number of ARP poisoning packets, we want only to take a look at the requests. To do that, we're going to have to use a filter that uses the attacker MAC address. To do that, we're going to have to use ethernet.destination. No, source, sorry. So source, since it is the machine making the request, it's going to be the source. 000C29E2 B4. So that is the source MAC address of the attacker. And we're going to use another filter. Since we want to take a look at the ARP requests, we're going to use ARP, and then the option will be opcode. There are many opcodes that would indicate different meanings. So an opcode of 1 meaning an ARP request. An opcode of maybe 2 would mean an ARP response. So here, as you can see, this is the final filter. We click enter, and we can see we have 284 packets. Next thing, what is the number of HTTP packets received by the attacker? Now this is easy because here we have the address, or the MAC address of the attacker. Now the attacker is on the recipient side, so this will be the destination. And we're going to use on the other side of the condition here, we're going to use HTTP because we want to filter for HTTP traffic. This will list all the HTTP packets where the recipient is the attacker. So we enter and we see these packets. So we have 90 packets. Next thing, what is the number of sniffed username and password entries? So since we are taking a look at the HTTP packets, there is a high chance since we're taking a look at the HTTP packets in here, there could be chances or there could be packets that contain username and password entries. So we're going to take a look at one example packet. So this one represents a GET request to a page or to a login page, login as you can see here. And there is a response from the server. So if we follow the stream of this packet, we're going to be able to take a look at the raw data. So following the TCP stream, this is the request and this is the response. Scrolling down, you can take a look at the body of the request. From the body of the request, we should be able to extract plain text credentials. So this is the TCP stream. I'm gonna have to go back. Exactly, that's what I need. And take a look at the HTTP stream. So here follow HTTP stream, and from here we see the response of the server. From here, if we search for a combination of username and password, okay, so if we search for maybe username, as you can see, we have the username and password submitted in the form, but we cannot see the actual values. To be able to see the actual values, we're going to have to, make the filter more narrowed. So going to modify the filter. So here, as you can see, the request is made to this host, and this is the web page, and it is a GET request. Usually, the credentials are revealed or are sent to the server using a POST request. So you're going to have to filter the HTTP traffic for a POST request, and we're going to use this host as another filter. So we're going to copy this, go back, and from here http.host equal to this host, okay, and http.request.method equal to post. So in this filter, we are using the HTTP traffic, HTTP filter. As part of the HTTP options or the attributes that can be used with the filter, we have the host. We can filter by the request method. So we're filtering for the packets that are sent or that have the host in the packet equals to this host, and the request method equals to post. Now, of course, you can change this to get, to delete, to put, depending on the kind of request you're looking for. You're gonna hit enter, and this would reveal all of the post requests. So you have a post request here to user info, and the following packets are all representing a post request to the web page. Let's take a look at an example. Follow the stream, and we scroll down here. We want to see patterns, username and password. Let's use a filter, username, or maybe pass. Okay. So we have one, username equal test and password equal to test. You can see more examples. Okay, this is another one. That's another request where the username was uname equal to test underscore thm underscore test, and the password was insecure pw. So these are tests. I don't think they are counted as the answer. And then we have these are also tests, Okay, let's take a look at this one. So that's a username, MITM, that's also a test. Okay, this one, test underscore THM underscore test, insecure password, admin super secret, client, and we have client 354, nice work. So in total we have around 6 usernames and 6 passwords, so we have 6. What is the password of the client? 986. So we are in the same pane here. We're going to take a look at this. So that's the client 986 and the password is the client not there. What is the comment provided by client 354? We're going to go back to the last packet. You can see the client 354 and the comment was nice work. Alright, next, identifying DHCP, NetBIOS and Kerberos traffic. So going right to the questions, going to open this PCAP file. So from file menu, open, and we go to DHCP, NetBIOS, Kerberos, highlight the DHCP, NetBIOS PCAP. So that's the captured file. Okay, all right. So what is the MAC address of the host Galaxy A30? So we are given a host. We want to find out the MAC address of this host. Remember that when we analyze DHCP, NetBIOS or Kerberos, most likely the information that we will extract are information that identify the endpoints, such as the host name, the source, and destination MAC address, the IP address. So when we analyze DHCP, NetBIOS, Kerberos information, we aim to extract host name information, IP, MAC address, or even username information when we analyze Kerberos. So we're asking, what is the MAC address of this host, Galaxy A30? So the host name of every single machine is transferred through the packets when the client or when there is DHCP, NetBIOS or Kerberos protocol in the traffic. So most probably if we're gonna search with this host name, we're gonna be able to find it in these packets, okay, because they are DHCP or NetBIOS traffic. So we're gonna use the search feature, so edit and find packet. We explained this previously in the previous video. So for the packet details, we're gonna keep this as is. We're going to use string search and type Galaxy A30. We search with this, click on find. No packet contained that string in its dissected display. Oh, that is strange. Let's make sure we open the right file. Go to statistics, captured file properties. You can see we opened the right file that represent the NetBIOS and DHCP traffic, yet we seem to get only the ARP packets. Alright, okay, let's do this. DHCP. Okay, we have DHCP traffic, but still we cannot find the Galaxy A30. Let's search for NetBIOS, NBNS, and we have NBNS traffic or packets. Okay, so but we cannot find details about this host. Let me try the next question. How many NetBIOS registration requests does the Leva LJM workstation have? So we were looking to filter for NetBIOS packets. Usually, if you want to conduct NetBIOS search, you use NBNS. This would show all of the NetBIOS packets that have been captured. Now we want to extract the registration, NetBIOS registration packets. To do that, we're going to use the flags nbns.flags opcode needs to equal to 5. Again, guys, as with all protocols, there are opcodes that indicate the request and response for every single stage. For the NetBIOS, we have, as you can see, guys, 5 for the registration. Same with DHCP. Different opcodes for different stages during the life cycle of the request. So for request, we use opcode 3, option 3, and for response, we use 5. For denied request, we use 6. And these can be found here. If you take a look at an example, NetBIOS packet, going to the protocol breakdown, we can see here in the queries, the flags, we have the opcode, as you can see here. Okay, so opcode needs to equal to 5, and we're going to search with another thing, with the host name Leva LGM. So if you go to the queries here, we can see there is an attribute name. This indicates the host name of the machine that initiated the NetBIOS request. So we're going to use this attribute in the filter. So and nbns.name, it's not going to be equal, we're going to use contains, okay, contains filter, and this is the name we're looking after. Okay, good, we have hits. So how many NetBIOS registration requests? And we have 16. So no idea why I cannot find this host. Try it out, guys, and tell me your feedback in the comments. Which host requested the IP address? So here we need to analyze the DHCP packets because we're looking for information that belong to a machine initiated an IP assignment. So there was a machine that requested to have this IP address. So to find out this machine, we're going to need to take a look at the DHCP packets. Usually you can conduct global search to extract DHCP packets using DHCP filter. This would show all the DHCP packets. Again, guys, to be able to use the filters and the attributes of this filter, take a look at an example packet. And go back, or go to the protocol breakdown, highlight dynamic host configuration protocol, and from here we can take a look at the options. So these options can be used in the filter up here. We have the length, hardware type, client MAC address. All of these can be used in the filter. So we want to find out the requested IP address. Let's see if we have this option here, an option that we can use to filter by the requested IP address, because in a DHCP packet, a host will send a DHCP request for an IP assignment, right? Client MAC address, message type, parameter list. So this is DHCP inform. We're going to need to take a look at the DHCP request packet. Let's see here. So DHCP request packets can be found using this opcode 3. So these are the DHCP requests. Let's take a look now at the options and we can see here that option 50, we have this requested IP address. Now we're going to use this in the filter. So here, option underscore requested underscore IP underscore address equal to this. Let's see who's the host that requested this IP address. DHCP.option underscore requested underscore IP underscore address. The query tells me there is a problem. Let's see here. Dot requested, not underscore. And now it is correct. Okay, we have one packet. Take a look down here. We want to extract the host name. Scroll down. The host name usually is an identifier that can be found from here. So option 12, the host name is Galaxy-A12, which is the answer. Now, next question. What is the IP address of the user U5? We need now to analyze the Kerberos packet capture. So we click on File and we go to Kerberos. So these are Kerberos packets. In order to conduct global search with Kerberos, we can use, let's scroll down, we can use this keyword. This would list all of the Kerberos packets. Okay. Now, the same thing with every protocol. In order to figure out how to extract attributes from these packets, we're going to have to take a look at an example packet. We go to Kerberos, and we can see here the tickets. These are the options or the attributes we can use in the filter. So we have CNAME. This would indicate the host name of the machine and maybe the username of the machine. CNAME string. And we have ticket if you want to filter by tickets. So the question is here telling us to find out the IP address of the user U5. So usually we want to filter for the packets or the Kerberos packets where the username contains the U5. Therefore, we're going to use the CNAME string. So Kerberos.CNAME string contains U5. Now we have hits. So what is the IP address of the user? Let's take a look at an example packet again. Going to the protocol breakdown, you can see here, let's make sure the data is correct. The username is or contains U5. Okay, so CNAME string U5, meaning that this is the correct machine. We need to find out the IP address. The IP address is 10.1.12.2. What is the host name of the available host in the Kerberos packets? What is the host name of the available host? So we need to circle back here and use this filter. Why? Because we need to list all of the CNAME strings from the Kerberos packets. So take a look at the first one, for example, or this one. So the CNAME string here is DES. What is the host name of the available host? The question is vague, I may admit, because there are many host names here. Now this one contains the correct answer. Okay. So as you can see, guys, we analyze DHCP, NetBIOS, Kerberos packets to extract hostname information and other identifying information, such as the username of the machines. Now next, we're going to take a look at the task 5, where we're going to analyze DNS and ICMP traffic. Usually, DNS and ICMP traffic are used to perform tunneling, meaning used under the context of that, in the context of data exfiltration. After the machine is compromised, usually the attackers try to smuggle the sensitive data through these protocols, DNS and ICMP, to hide the what they are doing. Okay, so now let's expand here and see the questions. Investigate the anomalous packets. First, we're going to take a look at this PCAP file. So file, open, go to this one, and I'm going to analyze this. Okay, So investigate the anomalous packets. Which protocol is used in ICMP tunneling? All right, so to conduct global search to reveal the ICMP packets, we can use ICMP. Again, as with every protocol, we take a look at an example packet and we scroll down to the packet details. We see what kind of attributes we can use in the search. Data, the sequence numbers, all of these are valid options that can be used in the filter. So here we want to find out the anomalous packets. So usually an ICMP packet is anomalous when the length of the packet is more than certain size, which happens to be a standard size for ICMP packets. It is 64. When the length of the packet is more than 64, the ICMP packet is considered to be suspicious. It means it might contain data, more data than it's supposed to be, because ICMP is a protocol used to network troubleshooting and probing as well. So the data length of an ICMP packet is not supposed to be more than 64. So to find out the anomalous packets, we're gonna filter for ICMP and we're gonna have to use another filter. The data length here. As you can see, an example packet here, data length is 84 bytes. So to filter for packets where the data length is more than 64, we're gonna have to use this filter and more than 64. This will give me all of the packets where the length is more than 64. As you can see, an example packet is here. You can see the data is 84 bytes. And this one is the same 84 bytes, a total of 759 packets. So, which protocol is used in ICMP tunneling? We want to find out the actual reason why this packet is more than 64, meaning there might be some tunneling happening, it's going on here. So to find this out, we're going to take a look at an example here. It's not clear what kind of payload data is this. So we're going to need to take a look at more packets and keep an eye on the payload data on the right. Okay, stop there. Take a look at this one. So here there is OpenSSH, packet number 42. As you can see, guys, the payload data shows an OpenSSH banner, which means that the protocol ICMP is smuggling data using the OpenSSH. So the protocol used here is the SSH protocol. Now we're going to open the other PCAP file, DNS, analyze the DNS traffic. Okay, same with other protocols. We use DNS and we can find out all of the DNS packets. All right, so DNS is a very common and popular network protocol. Attackers use this protocol to conduct queries or to send queries to a C2 server, as we learned from the previous videos. So there is a high chance that these packets contain queries sent to C2 server in order to, request commands to be executed on the compromised machine. So we're gonna need to reveal the malicious DNS packets, or the packets that probably were sent to a C2 server. To find this out, we're gonna need to rely on the data length. So a malicious DNS query that's sent to a C2 server usually will look longer than the regular DNS query that's sent to a regular domain. To find this out, we're gonna need to use query attribute and name dot length. Gonna need to be more than 15, and we need to also satisfy this condition. So take a look at these packets. We have a total of 30,364 packets. The question is, investigate the anomalous packets. What is the suspicious main domain address that receives anomalous DNS queries? Okay, here we're gonna again need to take a look at the payload data. We have a lot of queries here. So there is a malicious domain you might probably need to take a look at many packets to find the correct answer. If you take a look at the payload data here, we need to find out a unique domain name. That's not so common. So keeping an eye on the payload data here, scrolling down, we can see this one, packet number 2621, and on the payload data section we see a domain name that equals to exfil.com. So that's the malicious domain. dataexfil.com. Next we can analyze clear text data transferred through FTP and HTTP. So here we go. Now I have FTP packets. Again, we can filter the FTP packets using the FTP filter. You can see all of the FTP packets. Same with other protocols. There are options, attributes that can be used, as you can see guys, to filter for FTP requests, FTP response, failed login attempts, successful login attempts. Now here to find out the brute force attempts as depicted in the question, we need to look for the correct code sent by the server. Usually brute force attempts have many failed login attempts. To filter failed login attempts, we're gonna have to use the response code sent by the server. Every packet has a response code. You can find it from here. From the protocol breakdown, you can see the response code attribute. It can be used in the query, as we have demonstrated with every other protocol. Okay, so ftp.response, and then .code has to be 530, indicating a failed login attempts. How many of them? 737. What is the size of the file accessed by the FTP account? Okay, here we're looking to extract the files accessed. So again, this is another FTP code. So the FTP code for file status or file probing is 213. So we're going back here and say instead of 530, it's going to be 213. And we have one. So we have two packets. We need to find out the size of the file. Okay, to find out the size of the file, we can see here in the info section, it is 213 bytes. File status 213. Oh no, I made a mistake. It's not that, it is this one. 424. That's the file of the size accessed. Adversary uploaded a document to the FTP server. What's the file name? We are in the same pane. We're looking to find status information about the files. So here we have this. We can choose to follow the stream, and we can follow along with the packets. Here you can see a login, successful login. Scrolling down, we see a list of the current directory to list the contents, and we can see a command sent to the server to upload this file, resume. So the file name is resume, or it's document file. The adversary tried to assign special flags to change the executing permissions of the uploaded file. Again, we are back here with the file status. Response code 213. So back here, follow TCP stream. So we're going to need to follow along with the commands that the attacker executed on files. Now we see this one, chmod 37. So that's the command used to change the permissions on the resume uploaded. Okay, now we can analyze clear text data on the HTTP protocol. Okay, close, open a new file. That's quite long room. Analyze the user agent pcap. Okay. So this is the pane, or this is the packet list of HTTP packets. Again, we can use HTTP to conduct global search of the HTTP packets. Now, usually guys, if you want to analyze malicious packets or malicious traffic sent over HTTP, One of the common signs is the user agent. So a malicious user agent is usually found through packets sent from the attackers. So the question here is asking, investigate the user agents. What is the number of anomalous user agent types? So there are many ways to answer this question. Usually you want to look for the most common malicious user agents. Okay, to be able to do that, we're gonna need to know what are these user agents. So we can take a look at an example here. This is an example packet. We go to the protocol breakdown, and from here we can analyze the user agent. The user agent here is Mozilla. That's not a malicious user agent. Usually it can be malicious. You cannot rule it out unless you analyze it more in depth. Take a look at another one. So take a look at this one. The user agent here is SQL map. Most definitely this is an indicator that an attacker is using SQL map to analyze the web application for SQL injection vulnerabilities. So upon analyzing, or when you analyze most of the packets, you will be able to come up with the list of the user agents used and to attack the host. So basically, let's see here in HTTP, we can extract them, or we can use this filter. So this filter here, we can analyze it. Okay, so here we're looking for the user agent attribute. So this filter will list all of the packets where the user agent equals to SQL map or Nmap or wfuzz or Nikto. So we have 24 packets. We want to find out what is the number of anomalous user agent. To facilitate this, we're going to have to add this as a column. So apply as a column, and now we have the user agent here. Another filter for the user agent can be this. So here would indicate that there is a log4j attack carrying this user agent, and we can see another one. This is the user agent used. This would now make them 3 user agents. And again, guys, we can use another query. Let's go back. Look at this one. We have a base 64 here. If you take a look at this, gonna copy that, copy the value, and go to CyberChef. From base 64. And this base 64 command is used to retrieve a file from the server, LH. It's a bash script, and it downloads the script, gives it execution permissions, and execute on the machine. Look at this one. So that's the user. That's an indicator of another attack was taking place. And this would answer this question, by the way, the last one. Now this one is interesting. There is a slight typo here. Instead of Mozilla, it is Mozilla. Now usually attackers use typos to deceive analysts. So if you take a closer look, or if you take a quick look at the user agents here, you will realize, oh, this is Mozilla, nothing abnormal here. But upon a closer inspection, we see a typo here. It looks very similar to the original name. Open. Okay, so where is this file? Come on, don't make it hard. HTTP. Okay, now we can use the same filter here and take a look at the packet number. The start is 444. This is the packet number. All right. Next, task 8, analyzing HTTPS traffic. We can conduct a global search for HTTPS data using HTTPS. Nope. SSDB. Well, it works partially. Maybe you can try with HTTP2. Okay, so why this doesn't work? Why we cannot filter all the HTTPS traffic? Because usually traffic sent over HTTPS is encrypted, which means we cannot have full visibility on the details, including the payload section or the payload data, other data such as the information transferred over the protocol. So we don't have full visibility over what data is being transferred when we analyze HTTPS. So that's why, in order to correctly analyze or to be able to have as much information as possible from the encrypted traffic, we're going to rely on the what's called the TLS handshake. The TLS handshake is the same as TCP handshake, but encrypted with the TLS protocol. As you can see here, guys, there are many states for the TLS handshake. So as you can see, a handshake, TLS handshake type 1, okay, and TLS handshake type 2. So type 1 when a client says hello to the server, and type 2 when the server says hello to the client. We can use these as well to extract the communication between the client and the server over the TLS or over HTTPS protocol. We can see these are requests from the client to the server. And if we use this filter, actually we only change one with two, we can see the server answers to the client, right? So this way we can filter HTTPS traffic relying on the TLS handshake. The question here is, what is the frame number of the client hello message sent to accounts Google? So you're gonna have to filter with the packets sent from the client. Okay, so look here, for example, this one, as you can see in the payload data section, we can see this accounts google.com. Now to be able to find the frame number, we're going to have to look at the packet details. So this is packet number 16. Decrypt the traffic with the keys log file. What is the number of HTTP2 packets? So what's going on here? Alright, so as you know, guys, this is an encrypted traffic. To be able to decrypt it, the only way is to have the correct public and private key. We have to make sure that we have the keys used to encrypt the session. As you know, guys, when you browse a website using HTTPS, as you can see in the browser here, there is a session open between you as the client and the other website or the server as the server side. This session, okay, uses pair of keys. If we cannot capture these keys, we're not going to be able to decrypt the traffic. Okay, so to answer this question, the author of this room has provided us with a key log file. This log file was created after they captured or they sniffed the traffic over an HTTPS session. When they did that, they were able to extract the keys. So with the keys ready for us, we can decrypt the traffic. Okay, so to decrypt the traffic, we're gonna X on this, go to File, Edit, Preferences, and then go to Protocols. I'm gonna supply Wireshark with the correct keys. So let's see here, looking for the correct protocol. It's gonna be long, no. So TLS is ready here, okay. And here the pre-shared key is what we need. The file contains the encrypted or the encryption keys. Okay, so we browse to the key log file. We already have it here. Gonna open and then click on OK. So now I provide Wireshark with the correct keys to decrypt the traffic. Next is to type HTTP 2, not 1 man, 2. Okay, and now we have the traffic decrypted. Now we can take a look at the packets in clear text, and there are 115 packets. Go to frame 332. Okay, we're gonna go to packet 322. That's right. Okay, what is the authority header of the HTTP2 packet. Okay, taking a look at the HTTP2, which is a decrypted form of HTTPS, scrolling down to the authority header. So that's the authority header, safe browsing googleapis.com. Investigate the decrypted packets and find the flag. What is the flag? Okay, so to find the flag, you're gonna have to export the objects. So go to File, Export Objects. Okay, as you can see, we have two. So we're gonna save the first one, desktop. And now as you can see, guys, we have the file. We open the file and we can see the flag here. Okay, last two tasks are very easy, guys, but I'm gonna go over them nevertheless. So here we learn how to extract clear text credentials automatically without the need to go over, filters and decrypt traffic. So we're gonna load the relevant packet capture file. It is under bonus. Okay, so go to tools, credentials, and Wireshark automatically extracts all clear text credentials transferred over non-secure protocols such as FTP and HTTP. You can see them in here, the username and additional information. Okay, so what's the packet number of the credentials using HTTP basic auth? We have only one that uses HTTP basic auth, and it is 237. What's the packet number where empty password was submitted? So as you can see, we cannot find out what password can be, what password has been used. But if you click on an example packet, let's take a look at this one. See, we are brought to the packet number 170, and we can see that there is no password provided, empty password. Okay, last one here. I'm gonna open the relevant PCAP. We are in the same PCAP file. This task is about creating firewall rules. So how is that possible? So basically, guys, Wireshark, based on the given PCAP file, it can give you defensive insights. So if you are using, for example, one of these firewalls, NetFilter, Cisco iOS, IP filter, Wireshark can create firewall rules automatically for you. All you have to do is to go to Tools, Firewall ACL Rules, and you can find all of the possible rules that can be created based on different attributes. From here, we can select what kind of firewall we want to create the rule for. We can select IP firewall, and from here we can see all of the rules that can be applied. So here we want to create a rule for denying source IPv4 address. So source IPv4, and we can use this one to deny the source IP address. Select packet number 231. Okay, packet number 231. This is the packet. Highlight the packet, go to Tools, Create Firewall Set, and here we can select again IP firewall. What is the rule for allowing destination MAC address? So here all of these are for IPv4. Scrolling down, we can see MAC address. We want the destination MAC address. So we want to allow destination MAC address. So we can use this one, but instead of deny, we're gonna use allow. So that was it, guys.